I'm watching the clock. That's right.
Plus or minus 5 seconds.
Okay, go. All right. Time to go. The clock. Yes, it now says 4 o'clock. So, thank you for your patience for these last 40 seconds. This is the annual Raymond Sackler lecture at the Center for Astrophysics. It's supported by an endowment provided by Raymond and Beverly Sackler. For many years, the Sacklers actually came for the lecture, but have not been able to do that for the last several years. And we're in for a treat today. Our speaker today, who's known to many of us, is Professor Lisa Kewley, who's Professor and Australian Research Council Laureate Fellow at the Research School for Astronomy and Astrophysics, previously known as the Mount Stromlo and Siding Spring Observatories at the Australian National University. Lisa got a Bachelor of Science with honours in astrophysics at the University of Adelaide, and went on to complete her PhD at the Australian National University in 2002. And we overlapped from time to time during that period because I was commuting to Mount Stromlo for the Macho project, but we didn't really become close. But after leaving Australia, Lisa became a Center for Astrophysics Fellow, and then went on to take up a Hubble Fellowship after that at the Institute for Astronomy in Hawaii. She went on to join the faculty at the University of Hawaii, and then in one of their coups, the Australians attracted her back, and she's now at ANU. Lisa is a specialist in the study of galaxy evolution, and she's going to be talking to us today about galaxy evolution in 3 dimensions.
Yes.
Lisa.
Thank you. Okay, so I'm going to be talking about galaxy evolution using integral field spectroscopy, and a lot of the work I'm going to be showing you today, credit goes to a great group of students and postdocs, many of whom are about to leave and go to all sorts of exciting places like Caltech and various Max Planck institutes. Now, just a summary of my talk today. First, I'll give a quick introduction as to why I'm studying galaxies in 3D in particular, and unsolved questions in the field, what we can do with integral field spectroscopy to solve these questions. And then I'm going to show you some of our recent highlights from a large survey that we're doing called SAMI, which is an instrument on the Anglo-Australian telescope. And we can study inflows, outflows, as well as we can dissect galaxies now into the different power sources, whether it's star formation versus AGN or shocks from outflows. And then in the later part of my talk, I'm going to talk about the early universe and how we're probing the early universe using Keck adaptive optics and near-infrared integral field spectroscopy. And we can look at how galaxies form their disks, as well as measuring outflows, again probing them using shocks. And finally, I'm going to talk a little bit about the future of 3D spectroscopy, in particular with the Giant Magellan Telescope, because you and me are partners in the Giant Magellan Telescope, except that our money is already on the table. Okay, it's true. Now, I'm trying to understand the evolution of galaxies from the distant universe 7 to 10 billion years ago until now. But the problem is, in the distant universe, we don't have a lot of information about the galaxies, and I really want to understand the physics inside galaxies and how galaxies grow and evolve with time. This field has changed dramatically over the past 15 years. Previously, and when I did my thesis, we got 1 spectrum per galaxy, 1 spectrum at a time, and we did about 10 galaxies in a night. And it took me about 6 months of observing to get a sample of maybe 300 galaxies. Things have moved a long way since then, but we're still using spectra to obtain huge amounts of information from galaxies. So this is the sort of information we can get from a typical spectrum. We can measure the metallicity, and we can use that using the oxygen lines relative to hydrogen lines, as well as the nitrogen 2 line. And the metallicity is the amount of metals. And for those of you who are not an extragalactic astronomer, what we mean when by extragalactic astronomer version of metals is we know we have hydrogen, we know about helium, but everything else is metals. And we probe metals by looking at oxygen. And this is actually not crazy because oxygen is the dominant element by mass and it's a temperature sensitive element. So these emission lines are very sensitive to the electron temperature of the gas. If you increase the number of metals, doesn't matter what metal, then they act as coolants in a nebula, and so you get less collisional excitations of the oxygen lines the more metals you add in the nebula. So it actually does probe the full amount of metals in a nebula. We measure the star formation rate, of course, using H alpha and O2, and we can measure the electron density using the sulfur 2 and oxygen 2 lines. We can have a look at the ionizing source, a power source within galaxies, using various emission lines that are sensitive to the hardness of the EUV radiation field. We can measure the ionization parameter, so this is how strong an ionization field is, and we define this in terms of the number of hydrogen ionizing photons per unit area per second. It's a flux divided by the hydrogen density. It's in units of velocity, so you can think of it as the maximum velocity ionization front that a radiation field is able to drive through a nebula. And then finally, we can also have a look at shock properties. And so these are shocks from galactic winds, typically, that we can measure. And we can use all these lines, again, to measure shock properties, shock velocities, metallicity in the shocked region, for example. Now, to use metallicity, we need to use diagnostics, and these are based on stellar population synthesis and photoionization models. And the models, what we do is we use metallicity as an input into the models, and then the different line ratios are an output from the models. And you can see some metallicity diagnostics are much better, much more sensitive to metallicity than others. This one's very sensitive to metallicity because nitrogen changes from a primary nucleosynthetic element at low metallicities into a secondary nucleosynthetic element at high metallicities, so it becomes more sensitive to the previous generations of stars. At the same time, the oxygen 2 line, as I said earlier, is sensitive to the electron temperature of the gas, so the oxygen 2 line drops while nitrogen 2 increases. This one's called R23. Lots of people use this at high redshift. It's not great because it's double valued with metallicity. So here the oxygen lines are just increasing with metallicity. But here the electron temperature is falling so fast. The cooling's being done by the fine structural lines in the infrared, and you get much less collisional excitations here of the oxygen lines. And so in the past we were able to derive these properties per galaxies. We made a very good measurement of the metallicity history of galaxies and the star formation history of galaxies, but we want to now move beyond global properties. And so what we're using is integral field spectroscopy, and we can actually probe using integral field spectroscopy inflows, outflows, star formation, as well as AGN. And we're aiming to answer lots of fundamental questions about galaxy evolution. So in particular, if you imagine a galaxy, this is called the bathtub model. You have some gas reservoir which is causing inflow into a galaxy. That inflow may trigger star formation, which then produces metals. The star formation may also drive outflows. We don't know how much metals are lost in the outflows, but some are in some galaxies. The gas inflow might also drive an AGN, which then may also drive outflows. And so there's all sorts of unsolved questions here. We really don't understand the detailed physics. And so we don't know when and how much gas is inflowing by what physical mechanism. We don't understand how common AGN outflows are or star formation driven outflows are and how much mass is lost. We don't understand fully how the metals build up in disks and then how much metals are actually lost during the outflows. We also don't understand whether there's a connection between star formation and AGN. We also would like to see whether this changes with time. So it's a complicated problem, and we can use simulations, but they don't actually tell us what's happening in galaxies, so I'm doing this observationally. Now, we can measure gas inflows and how much metals are being produced by star formation and how by looking at velocity maps and metallicity gradients in 3D data cubes. We can actually separate star formation from AGN using line ratios now. We can have a look at outflows through shocked gas. We can do that through velocity dispersion as well as line ratios. These provide an independent measure of shocks. And so I'm going to go through those. So first, we're going to talk about inflows traced through metals. So in a spiral galaxy, you have a typical large metallicity gradient. It falls in metallicity from the central regions to the outskirts. And with integral field spectroscopy, we don't just get a metallicity per radius. We actually get a metallicity map. So this shows you H alpha and oxygen 2 maps. And here is a metallicity map. This is based on the oxygen 3 and nitrogen 2 line. This is very sensitive to metallicity. And you can see that the metallicity changes from the outer regions to the inner regions. But there is some structure as well. For example, there's a little particle of gas here that's got a reasonably high metallicity. So there's interesting information in the metallicity gradients. And so what we did first was we measured a isolated galaxy benchmark gradient. If we're comparing other things to isolated galaxies, we need to know what is a typical gradient for isolated galaxies. So here's a metallicity gradient. 0 is a flat gradient, negative is a steep gradient, and we're using some different integral field samples here as a function of stellar mass. And if you plot metallicity as a function of kiloparsec, you actually see a change in the gradient, but that's not real. This is because galaxies have different sizes. And if you normalize by the 25th isophotal radius, you actually find that all galaxies across 4 orders of magnitude in stellar mass have roughly the same metallicity gradient. This is really interesting. This is telling us that they have very similar formation scenarios. Now, merging galaxies, when we look at merger models, they predict that you have large gas inflows into the nuclear regions down the spiral arms. And so here's a merger models by Paul Torrey. And so the merger models predict that at first close passage you have large gas inflows, and that causes a reduction in the metallicity in the central regions. You then have some rise in metallicity because the star formation triggered increases the enrichment, so it enriches the gas. And then at the late merger stages, you have final coalescence. There's another inflow of gas, which causes a second drop in the metallicity in the central regions. And then that metallicity rises again because of the star formation enrichment. At later stages, it's unclear what happens because if you have outflows, they're going to blow out the material. You won't have so much star formation, and you may never recover the metallicity gradient. If you don't have outflows, then you may recover a metallicity gradient. Okay, so we looked at a bunch of galaxies with Keck. These are galaxy pairs, and each of the dots shows where we put a Keck spectrum. And this shows the metallicity gradients. Here are the gradients versus radius, and they've been normalized by galaxy size. And the solid lines show you the isolated spiral galaxies, M101, Milky Way, M83. They have the same gradient as I just showed you, our benchmark gradient. And then all of the dotted and dashed lines are the gradients in our pairs sample. So all of the pairs have flatter gradients than any of the spiral galaxies. And this is really a smoking gun for these gas infalls. And at the time, these were very hard to measure. This is the first time we'd measured this systematically. And then we wanted to have a look at late-stage mergers. Late-stage mergers are more compact. We need integral field spectroscopy, and this was part of Jeff Rich's PhD thesis. And so he observed a sample of 40 luminous infrared galaxies with our ANU 2.3 meter wave spectrograph, and then plotted the gradient versus merger stage. And so this is isolated galaxies have a range of steep gradients. Wide pairs have smaller, flatter gradients. Close pairs, even flatter gradients. Late mergers, very flat. They're consistent with 0 gradient. And so this is showing you that mergers drive these pristine gas into the galaxies and flatten the gradients so that we can use gradients to trace mergers. You can, if you have a galaxy and you've got a flat gradient, chances are it's had some dynamical disturbance where you've had gas flows. Could be inflows or outflows that cause a flattening of the gradient. This has also been seen in many other samples now. This is just one of them. These are metallicity gradients in quasars. And you can see that in the major merger, you have an inverted metallicity gradient. And in many quasars, which are the remnants of a sort of a Lurg merger, then you also have some flat gradients. Now, we had lots of late-stage mergers in our sample, but we couldn't measure metallicity gradients in them. And the reason we couldn't measure metallicity gradients in them is they're galaxies like this, and they've got a large amount of outflows. So I'm going to show you how we now dissect galaxy outflows. And I'm going to start with mergers, and then I'm just going to show you isolated galaxy case. So in our mergers, these are the line ratios that we see. In the outer regions, they have high line ratios. S2H alpha is high, O1H alpha is high, N2H alpha is high. Almost all late mergers have this. And this is suggestive of shocks, although it doesn't prove it. But what we can do is, in each of the emission lines, we have very high spectral resolution in the red. So we can actually separate the emission lines into one and sometimes into 2 or 3 components. And so we have a broad component and a narrow component. We can do that for all emission lines, including the oxygen 1 line, which is weak. And then we can plot the velocity dispersion of the lines. And you can see they're bimodal. I'm going to switch pointers. Do people have trouble seeing the green pointer in the back? They're right? Okay. So you can see the bimodal distribution here. We have velocity dispersions which are large. These are 100 to 200 kilometers per second. These are typical of slow shocks. And then we have a velocity dispersion peak, which is small velocity dispersion for around 40 kilometers per second. This is really typical of H2 regions. So now we can do interesting things. So we can color code our shocked regions and our H2 regions and see where they lie on the optical diagnostic diagrams. And so the starburst points indeed lie in the starburst region, the H2 region part of the diagnostic diagrams, and then the broader component lies offset into what we used to call the composite or the liner region, and this is typical of shocks, and we know that because we do starburst and shock models. These are using our mappings models. The blue line shows you pure star formation, and the red line shows you pure shocks, pure star formation and pure shocks. And the different colours show you mixing. So these are mixing sequences between the pure star formation and pure shocks. And they look different because these galaxies had 2 different metallicities. We've got a high metallicity galaxy here and a low metallicity galaxy here. And so the shock models lie right on the data. You can see that in some cases you've got a lot of mixing between the star formation and the shocks. And each spaxel has a different ratio of mixing between star formation and shocks. With these we can isolate how much shock contribution there is to each emission line, and because we can resolve it into a broad and a narrow component. And then we can measure things like the fraction of total H alpha versus merger stage, which has a contribution from shocks. So in the isolated merger stage, we have mostly star formation dominating the light. At wide merger stage, wide pair stage, it's still mostly star formation. And so this is the shock component, and the blue line is the H2 region component. Green is some intermediate component that we sometimes pick up in some galaxies. At the close merger stage, you've got roughly the same amount of star formation to shocks, and then at the late merger stage, these are when galaxies have got a single nucleus, but they've got some tidal remnants of the merger. You can see there's a large amount of shocks. They actually contribute 70% of the H alpha emission, which is why it's very difficult to measure metallicity gradients in these galaxies. We need to use shock models, not H2 region models, to measure those. These shocks are coming from star formation, not from AGN. These are in luminous infrared galaxies, and so we've got star formation driven outflows from these galaxies. We can also measure shocks in isolated galaxies, and so these are done with the SAMI survey. SAMI is a southern version of MANGA, but we were first, and we're measuring 3,000 galaxies with integral field data by 2017, and then in 2025 we aim to have 100,000 galaxies. We've just been given a grant to begin the building of our Hector spectrograph, which is going to be a robotic piezoelectronic positioner for our fibre bundles to measure this sort of number of integral field data cubes. So this is an example of the SAMI data. The advantage of SAMI is that it has high spectral resolution in the red, so it has a red arm and a blue arm, and so we can choose different spectral resolutions in the red and the blue. So we choose a low resolution in the blue so that we can cover the broader wavelength and get the O2 line, because that's sensitive to metallicity. And then in the red we choose a R of 5,000, and that allows us to do this beautiful line decomposition so that we can measure shocks. And so this shows you that we can deconvolve the lines into 3 components. We have 2 narrow components and a broad component. And we can even do this using the sulfur 2 lines. Here's the sulfur 2 lines. And when you look at the velocity dispersion profile, you can see the narrow component, the H2 component that we saw earlier. Here's a shock component, and this is some intermediate component here. And so what's nice about this is now we have a new way of diagnosing shocks. You can plot velocity dispersion versus a line ratio, N to H alpha. If there's a correlation, you can't get this from beam smearing. This is clear indication of shocks. And so the shocks lie up here at the high velocity dispersions, around 200, 300 kilometers per second, and then the H2 region. And now we can do really nice things. So remember that. And here, these are the velocity maps of the shock component and the H2 region component decomposed. So this is the H2 region component. We've got a nice rotation map from the galaxy. Here's our shock component. Okay, so the shock is coming out in the opposite direction to the rotation of the galaxy. And then the intermediate component is some combination of the two, and we think it's some sort of shear region. We're seeing shocks all over the galaxy, but primarily coming out in the opposite direction to the disk. So this is very beautiful. What we're doing now is applying this to the full SAMI sample and trying to understand how much shocks there are, how much mass is lost in the shocks, and what's the mechanical luminosity of the shocks. The other thing we've been doing with the integral field data is to separate star formation from AGN. So when I did my thesis back a long time ago now, the aim of my thesis was to do star formation versus AGN in luminous infrared galaxies, but I remember I observed these with the 2.3 meter telescope, and we only had a single spectrum per galaxy, so you actually can't discriminate between the starburst and the AGN. A single slit or a single fiber is not enough. So now we can do much better. So recall, this is the standard optical diagnostic diagram. Here we have the star forming sequence, and here's the AGN sequence. And these were 85,000 galaxies from Sloan. Now what we're going to do is going to look at the same sequence, but only in one galaxy at a time from our Wave spectrograph, and looks the same, right? We've got mixing between starburst and AGN, and this is just spaxels, spatial pixels in the one galaxy. And so now we can do really nice things. So if we can ask, say, for example, how far out does the AGN narrowline region go? Where are these? Okay, so where are these points? They lie in a ring. Beautiful. This is the narrowline region radius. Okay, because beyond this we have pure star formation, and above this line it's dominated more than 50% AGN. We can do better. If we now dissect the line ratio diagram into different positions up this sequence, you get more rings. Okay, so here we are dominated above 90% AGN. In the green, we have 40 to 60% AGN. The red is roughly around 30 to 40% AGN, and the black is dominated by star formation, pure star formation. And so what this means, this is a really powerful technique. What this means is that we can actually separate for every line, for every spaxel, what is the contribution from the star formation and what is the contribution from the AGN. And this is the first time we've ever been able to do this. If we could have done it in my thesis, I would have been able to answer my thesis question. Now, the way we do this is using, we can do it empirically, or we can use theoretical models. We do both. So here we have our starburst models. And these are from combining the stellar population synthesis models with our mappings photoionization models. And the different colors correspond to different metallicities and different ionization parameters. And you can see that we have a nice starburst sequence. In pure star-forming galaxies, we typically see a curve along here for these galaxies. And then with our AGN, we use our AGN models. We're using the same mappings models, so they're self-consistent with the starburst models. And then we can measure the ionization parameter as well as the power law index. We apply these to each galaxy, and we're in the middle at the moment of applying them to all the AGN in the SAMI survey. These are just teasers, so we can actually divide the mixing sequence into even more components, 10, and we actually see in some cases 10 rings all the way out. And so this is what it means. We can measure the narrowline region radius. We can measure the AGN contribution to each line. We can subtract the AGN, and then we can measure the star formation rate without contamination from the AGN and the optical. We've done that, and we've compared it with infrared as well as other wavelengths such as radio, and we can reach agreement now from a galaxy that contains a whopping great big AGN, which is excellent news. And then the next step is to measure metallicities in galaxies containing an AGN without contamination from the AGN. We can subtract the starburst from around the AGN region, and then we can measure an AGN luminosity and Eddington rate without contamination from the star formation, and we can measure the AGN narrowline region properties once the star formation's been removed. So we're in the process of doing these next steps right now. So I'm just going to show you also what we can do at high redshift. And so we're using gravitational lensing because we need to get about the same spatial resolution as we're doing locally with our SAMI survey. But at high redshift galaxies, we just don't usually have the spatial resolution unless we use gravitational lensing. So gravitational lensing is a very powerful technique, and the light's bent by lensing mass, but the light is distorted in all sorts of different ways. And so to actually measure spatial distributions of emission lines, we need very good lensing mass models. I'm just going to give you an example. Okay, so here's, you should know this building. We're going to lens it. Okay, so imagine this is our galaxy. We've got a double image of the galaxy. It's upside down though, and all distorted. And this bit's a double image of the ground. And so we have to use our lensing mass models to get back to this sort of thing, but using a galaxy so that then we can measure metallicity gradients. And so that's what we're doing. And at the moment we start with easy cases, and this is an easy case. So this shows you a grand design spiral galaxy. It's a redshift 1.5. And this galaxy would be this size if it wasn't lensed. And it's magnified about 5 times on the side and about 30 times in magnitude. And it's not significantly distorted by the lens. So here's an example. Here's the image plane of the galaxy, and here's the source plane, and they look pretty similar. The gravitational lens is basically just doing this to the galaxy. So we're lucky in this case. Some of the cases are much harder to model. And so what we did with this galaxy, we measured its metallicity gradient. So we went with Keck Osiris and adaptive optics, and we measured the N2 to H alpha line ratio. And here's the metallicity gradient up here versus radius. And this is in kiloparsecs because the other galaxies that we had were only measured in kiloparsecs. You actually couldn't measure a 25th isophotal radius or any other isophotal radius, but we did with our galaxy, and you get the same result. We found a steeper metallicity gradient than in local galaxies, and this was seen as evidence of inside-out disk formation. So in inside-out disk formation, the star formation occurs in the center, enriches the gas in the center of the galaxies, and slow infall causes slow enrichment of the metallicity in the outer regions of the galaxies, and typically you end up with a steep metallicity gradient. And so many metallicity gradients have now been measured. So here are metallicity gradients, and 0 is flat, and negative is steep, so there's not that many steep gradients. And they've been measured using all sorts of different ways. And you'll note I do not have a x-axis. Okay, what do you think that is? Could be year, mass, I don't know. No, it's full width half maximum angular resolution. Okay, so this is a bit of a problem. Here we have the steepest gradients are measured with the galaxies with the highest angular resolution, okay, and then flat gradients are measured in galaxies with lowest angular resolution. And so we modeled this. We used a nearby galaxy where we have measured the gradients in individual H2 regions. We know what that is, and then we reduced the resolution, and so we smeared it and measured the metallicity gradient, and it marches on up like this and becomes flat. And we also did it with our spiral galaxy. And again, when we degrade the angular resolution, the metallicity gradient marches on up and becomes flat. So what this means is that any of these measurements without lensing and adaptive optics, they actually can't measure metallicity gradients. What's causing the flattening is probably 2 reasons. One, you're introducing a lot of noise when you're smearing light out. They're measuring them in annuli, so binning in annuli. And so you're introducing a lot of noise, but also in spiral galaxies, there's a thing called the diffuse interstellar gas or the warm interstellar medium. And this is light that escapes H2 regions and then ionizes the surrounding gas. And this radiation field, it can be reasonably hard. It's absorbed by the H2 region. And then, so it can be strong in N2. And so this can contribute very strongly, particularly in the outskirts of spiral galaxies, to what you would measure as a metallicity gradient and can cause it to just become flatter and flatter and flatter if you don't have high enough resolution. This is what's happening here in these galaxies. So now many galaxies have been measured with adaptive optics. The ones with adaptive optics are these ones here, the squares. This is not my paper. I wouldn't have put the diamonds on here, which are not adaptive optics measured galaxies. But you can see the ones that have been measured with adaptive optics, there are all sorts of gradients. There are a few steep ones, but there are actually a lot of flat ones as well. And the solid points here are ones that are rotation dominated, so spiral-ish galaxies. And the ones that are unfilled are galaxies that are dispersion dominated, and some are clearly in mergers. So the effect of environment is really key in trying to understand these metallicity gradients in both in high redshift galaxies. And we know from local galaxies that we have a flattening of the metallicity gradients from in mergers, and this is probably what's happening in many of these cases here. But there's one more way of producing a flat gradient or even a inverted metallicity gradient, and that is from outflows. Okay, so this is an example of a lensed galaxy, maybe merging, hard to tell at high redshift. Very difficult to measure a velocity for this galaxy. This is the HST image and this is the source plane, so difficult. Now what we did was we looked at it with Keck adaptive optics again, and here shows you the different apertures that we were able to measure emission lines in, and I've isolated this B region here. And so here's the N to H alpha ratio as a function of physical scale on this galaxy. And you can see here that we have fairly flat or even an inverted, you could call this an inverted metallicity gradient if you used N to H alpha to measure metallicities. But the thing is that these points up here that are high, they're coming from this B region here, and this is the velocity map. Okay, so they look similar, don't they, to the galaxies I showed you previously with winds. Okay, so this is an outflowing region. It's coming towards us, and this is where the highest N to H alpha is, and it's in the outer parts of the galaxy, like our local wind galaxies. Looks very similar. And so we think this is a wind coming off this galaxy, and these are shocked emission. This is the first time we've seen shocked emission in a high redshift galaxy, and causing what would be interpreted as an inverted metallicity gradient. Now, we know at high redshift that there's winds in many of these galaxies. These are big galaxies, and they're dominated by winds. Sometimes 70 to 80% of them have winds. It's likely that they're going to have shocks in them as well. Not all winds drive shocks, but if you do have winds, then it's likely that you'll have shocks. And so here's just an example of comparison between the line ratios and our shock models. And you can see this is where this galaxy lies. We don't have O3H beta for this galaxy, so we can't, put a point on here, but it lies in the region where our shock models lie, and not in the pure starburst region here, shown by the blue. And so, and again, these are our mappings of shock models. And so this would originally have been interpreted as a shocked outer region or an inverted metallicity gradient, but actually it's actually shocks, we think. And so need to be very careful at high redshift when measuring metallicity gradients and interpreting them as some sort of evolution. There are lots of models at the moment predicting either flat gradients or steepening gradients with redshift. Whether it steepens or flattens depends critically on the wind models that are being used, and it's very uncertain at the moment. So I'm going to go through a set of conclusions. I know it's early. I realize I've gone pretty fast, so that means there's a lot of time for discussion. But I'm also need to talk about the Giant Magellan Telescope and some simulations that we've done. So this is actually not the end of the talk. Okay, so for local galaxies, I showed you that there's metallicity gradient flattening, and we can see this with integral field data, and then that's a signpost for inflows. And we can see it in merging galaxies in particular, and all mergers we looked at had a flatter metallicity gradient than in isolated spiral galaxies. I showed you that in outflows, shocks are dominant. We see them from outflows at late merger stages, and that they're starburst driven. And I also showed you how we can separate shocks from H2 regions in our SAMI data, and that was for an isolated spiral galaxy. And this is just the beginning of this work with our integral field large survey SAMI. I showed you that we can separate star formation from AGN, and that we have really clean mixing sequences, and we can separate the starburst from AGN in each emission line. And we find that, of course, AGN dominates in the lines traditionally dominated by AGN, the ones that are sensitive to the hard ionizing radiation field, like O3, and the starburst dominates more in the Balmer lines. At high redshift, there's a diversity of metallicity gradients that we see at the moment, and the environment and the effects of feedback are really key for this. And I don't think we've reached any sort of conclusion about metallicity gradients or evolution at redshift at the moment. I wish I could show you something different, but we need to understand environment and feedback. The gradients correlate with angular resolution, so if you're on attack and people are trying to measure metallicity gradients, they need AO and they need lensing. We can't do it at the moment with modern telescopes without the high angular resolution that you obtain with adaptive optics as well as lensing. We measured the first shocks in a high redshift merger galaxy, and this would mimic an inverted metallicity gradient. But although we can't measure metallicity gradients in shocked galaxies, we can probe galactic wind outflows, and if we can measure the velocity dispersion, we can measure the velocity of the outflow. So this is actually just the beginning of a new field. So I call this galaxy dissection. We're just starting to do this. With our SAMI survey, we have 2,000 galaxies in hand, and this allows us to do this galaxy dissection statistically for the first time. So we can do it for large numbers of galaxies, and we can even isolate subsamples of galaxies to dissect. And what I really like about this is we can get to the physics of what's really happening in galaxies, and when we're not contaminated by all the sources like we were in the past. So, for example, if we want to understand fueling of a star formation or AGN, then we can use both metallicity gradients and gas kinematics, the velocity maps I showed you earlier. If we want to understand feedback and outflows and measure physical quantities from those outflows, then we can measure the shocks as well as looking at kinematics. If we want to separate star formation from AGN, we can use the line ratio mixing sequences in combination with the morphological information, so line ratio maps. And then if we want to measure the AGN properties, then we can look at line ratios as well as AGN models. Same goes for the starburst models. And so we're at the beginning. This is just the beginning, and it's an amazing field to be in and to see this progress. In the very near future, we're going to have a survey called Wallaby in Australia, and Wallaby is a H1 survey that's about to be started with the SKA Pathfinder called ASCAP. And there's a large number of radio telescopes. They're still putting up antennas as part of Wallaby, and the survey is soon to begin, and the aim for this survey is to produce H1 data cubes, and it will have H1 data cubes for the same galaxies as in SAMI. So this is very powerful. What this means is we'll be able to have neutral gas, we have the ionized gas, and we have the old stellar population all in data cubes. And because we have the velocity information, we get a handle on the dark matter in the galaxies. And so this means that we're actually probing the separate phases of the matter in galaxies. If we can do this as a function of cosmic time, then we're probing the build-up of matter, and we can probe up the build-up of metals in galaxies as a function of cosmic time. So this is the beginning of a new field. We need to join radio astronomers with optical astronomers. We've just hired a radio astronomer at our observatory, and she feels a bit alone because we're optical, infrared, and theorists. But it's just the beginning of, to answer these really big questions, you can't just use one wavelength anymore. You need to combine all the wavelengths you can get hold of, and you really do need to go 3D. Now, in the more distant future, we have the GMT, and at ANU we're building GMTIFS for the GMT, which is the adaptive optics-led near-infrared integral field spectrograph. So we've been doing simulations with what we can do with the GMT, and I'll show you a simulation in a minute. At redshift of 2, we'll be able to measure detailed metallicity gradients So much better than we can currently do. And we can look for shocks, star formation and morphology. And this is in non-lensed galaxies, because right now we have a problem with lensed galaxies, is that they have to be at the right orientation. They have to not be too complicated for the lensing mass models. There are some lenses which are so complicated in the stretching that it's very difficult to reconstruct them, and then the metallicity gradient becomes very uncertain. You're not quite sure whether the radius you're measuring is the radius. Sometimes we don't even know where the center is. And so we'd rather do this without gravitational lensing, and with GMTIFS we'll be able to do this at redshift of 2 large scale without lensing. At redshift greater than 3, we're still going to need to use lensing, and we're working on UV diagnostics at the moment, because UV diagnostics are going to become much more important in the very near future, both JWST as well as the GMT, because that's the only way we're going to be able to probe the highest redshift galaxies. With JWST, we'll be able to probe UV diagnostics out to redshift of 6. And we'll also be able to use optical and UV between redshifts of 4 to 6. There's going to be a very, very powerful technique. And in the UV, we don't just have oxygen, we have carbon and nitrogen as well. So we'll be able to do a fully nucleosynthetic understanding of galaxy and how they build up their metals. Okay, so here's a simulation with the GMTIFS spectrograph. This is our lens spiral galaxy at redshift 1.5, and this was with a 5-hour net exposure on Keck Osiris. And this is what we're going to get with GMTIFS. And you can see that you can resolve the individual star-forming regions much better than we can currently with Osiris, but where the real power is in the weaker lines. So this shows you Keck Osiris, the nitrogen 2 lines, and at the moment we actually can't measure, it's not strong enough, these are less than 3 sigma, so we have to bin in annuli, and when we bin in annuli, we get an inaccurate metallicity gradient because of the diffuse ionized gas. We really want to just measure the metallicity gradients where we know we've got star-forming regions and not include the emission from all this surrounding material. Otherwise, our metallicity gradient becomes flatter. So our steep gradient is actually a upper limit. It could be even steeper. Here with GMTIFS, you can actually measure the N2 now in individual star-forming regions at the same redshift. Okay, and this is going to be very beautiful for doing for large numbers of galaxies. And that's the end of my talk, and I'll take questions. Thank you.
What is the thermodynamic state of the gas that you pick up as being shocked?
Well, it's thermally excited. The shocks are thermal. So I don't know if that's what you mean.
Is it that those atoms have definitely collided in a supersonic
okay.
shock?
So the shock has 2 components. So you have the shock where you've got the gas colliding with the other gas, which has formed the shock front. So we see some emission from the shock front itself. And so this is highly ionized, highly excited gas from the shock front. And the shock front produces a particular type of radiation field. But we also see a different type of gas which is a result of the shock. So the shock itself produces an ionizing radiation field in the X-rays and the EUV, and it's very strong. And if the shock velocity is greater than about 300 kilometers per second, that goes out in front of the shock and pre-ionizes the gas, and this is what we call the photoionizing precursor. And so that emission, because it's a very hard radiation field coming out in front of the shock, that produces these very hard radiation field, which means that we ionize nitrogen 2, S2O1, and oxygen 3 very strongly. And so if you have a fast shock, you produce the precursor, and we don't know what relative ratio we have of the precursor and the actual shocked gas, which is coming from the shock front itself. We usually use 50 to 50, could be anything. And if the shock is traveling at a slower velocity, it's not enough to produce a large precursor. And so then we just have the ionization, which is coming from the shock front itself. And this has lower oxygen 3 and lower amounts of into an S2, but it's mostly affecting the O3, and it's just because the shape of the radiation field from the precursor is hard, and the shape of the radiation field from the shock front itself is a little bit softer. All harder than a starburst, though.
Right,
So there's multiple components, and we have to iterate with the shock models.
But isn't it just essentially a small fraction of the total mass of the interstellar medium?
Oh yeah, we're looking at ionized gas. Yeah.
Ionized at the moment.
Right.
It's a
Exactly.
tracer
That's true.
of supersonic activity in the interstellar.
Right. It's a probe of the fact that you have in these cases, it's a probe of the fact that you have a wind. In some cases where we've got mergers, we see a shock front at the disk collision site, and so that's when the disks are merging. And then we're starting a zoom survey where we're using Keck Osiris to go right in the centres of some of these mergers to see what's happening. Why are we producing shock emission in the centre as well as the outskirts? And in the centre, what we often see is that the shocks are coming from either the collision site between the two nuclei, or shocks are coming out from one of the nuclei, and likely to be from the narrowline region, jets coming from an AGN. So there's multiple causes of the shocks in these galaxies. It's sometimes it's not just one. Yeah. The higher resolution you have, the better.
I have a question about the spectroscopy.
Mm-hmm.
So a significant fraction of the heat loss, if I remember rightly, from metals actually just come out in the fine structural lines.
Yeah.
Is there any prospect for starting to go after them at the same time?
Yeah, they're in the infrared, mid-infrared. So for some galaxies, we do have the fine structure lines from Spitzer. And in fact, with this GOAL survey, the ULERG survey that we did, we specifically chose those galaxies because they have Spitzer data. And my student, Jeff Rich, wrote a paper where he was comparing the shock lines in the infrared and the optical. And he found that indeed, where you expect to see shocks in the infrared compared to the optical, you do. They're very strong, these lines, particularly because these are high metallicity galaxies. So they're doing lots of cooling in the infrared. And so you'd like a larger sample, though. I mean, right now we're mostly doing this statistically using SAMI, and so you'd ideally have 3,000 galaxies, but there's no hope, unfortunately, of getting that with Spitzer. You need the high spatial resolution as well.
Do you see any correlation between the occurrence of helium-2 and the incidence of shocks? Because if the stellar wind driven, presumably there's a large population of pulsars, which might increase the strength of helium-2.
Yeah, it's a weak line.
Could you repeat the question?
Okay, the question was, do we see incidence of helium-2 associated with the shocks? 4686 is very unfortunate in that it's a weak line, and also for most semi-galaxies, it's actually in between the red and the blue. So we, I wasn't involved in the design of this, but it's right in between, so we can't actually observe it, unfortunately. Yeah. It's the same with the WIVE survey, because we're doing a red arm and a blue arm, and we want high velocity resolution in the red. That cuts our wavelength coverage off. So sometimes we can't measure it, but we have seen it. I think it was Jeff Rich was looking for it in his data, because there we can control the coverage a bit better. But yeah, we have seen it, but it's not a major project. It is a weak line.
It is an interesting line to characterize, because once you start taking the spectral high-rich galaxies, presumably you're going to get 1640 of them, and
Yeah. The other thing we have seen is in the near infrared we've looked, and we see the H2 to bracket gamma ratio is high in the shocked regions as well. So that there's another test that we are indeed seeing shocks.
Ramesh?
So, inflow, you said the big signature you talked about is the flattening of the metallistic gradient, right? Mm-hmm. But as you mentioned towards the end, there's also kinematic signatures of inflow.
Yes.
Did you show that in any of your pictures?
No, because most of the metallicity gradients that we're looking at were using single slits, so multi-slits on Keck, because the mergers are very big. And at the galaxy pair stage, it's large, so we couldn't use integral field spectroscopy, so we didn't get velocity maps for those. For these late merger stages, we do have velocity maps, but they're driven mostly by the shocks. So they're not at the stage where we think we're seeing the inflows. The inflows happened. So the inflow stage where the flattening happens very quick. So it goes flat, may go up again, flat, and then we have outflows. And we're seeing that dominates the velocity in the later stages. So it's just because of the samples that we picked and how we observed them that we weren't able to do that. With SAMI, we will be able to do that. We just haven't started to do that project.
But you think
yet.
it's a short phase?
I think it's a short
You have to be lucky
phase.
to catch it.
Yes.
Okay.
Yes.
I have a couple short questions. First of all, there's been this widely accepted statement that dwarf irregular galaxies did not possess metallicity gradients, and according to your figure in the beginning of the talk, they are all the same as the large-scale disks.
Right.
So where does it stand now?
So we didn't go to really dwarf galaxies. We went
Like
down
galaxy.
to we went down to 10 to the 8, but it's true they all lie on the same relation. So they don't have any different gradient if you normalize by mass than the rest of the galaxies. We'd like to push it down to smaller dwarf galaxies, and we tried. We did a survey with WISE before we started this with SAMI and some of the other surveys. We tried to get metallicity gradients for dwarf galaxies, and these are really dwarf galaxies, but the signal noise is not great for the emission lines in the dwarf galaxies. It's very hard to measure a gradient, actually, and need to integrate for a long time. So there's not a lot of data out there where you can actually do that, and you need to be able to also measure an isophoto radius.
And my second question, is there clear line ratio diagnostics to separate shocks from H2 and or AGN stuff?
Yes, so we're working on that now. I didn't show you a plot because it's in a paper in preparation and we're still playing around with it. But what we're doing is we're plotting, so we're trying to use all the information available in the integral field data cube. So we've got velocity dispersion, A line ratio, S to H alpha is a really good one, and radius. And with those three, what you see is you see a plane where the star formation is, and it curves, and then peeling off from that you can see shocks, and if there's an AGN it peels off in a different direction, because where you see the shocks is typically in the outer regions. Just for this data, because we're not probing the central regions at high spatial resolution, it'd be different if you were doing that. And then the AGN peels off in a different direction, because the AGN has high ratios at low radius, and the shocks have high ratios at high radius, and they do have different velocity dispersions. So the star formation has the low velocity dispersion. Shocks are typically 200 to, they can go up to 500 kilometers per second, but the AGN can be between 500 and 1,000. So this 3D diagram is a nice way of doing it. The thing is, you can't just come up with one line and have it used for every galaxy, because the different metallicities, the different shock velocities, the different ionization parameters, and the different AGN radiation field, power law, for example, produces different positions. And so you actually need to be able to fit this starburst curve, and once you take that off, then you can isolate them. But we haven't found an automated way of doing it.
And basically for aperture measurements it's hopeless.
Oh yes, and yeah, don't use single apertures, definitely not.
Okay, let's thank Professor Kewley again.